Hello, AP Chemistry. This is going to be my first attempt to record a lecture and post it on YouTube. This is the introductory lecture for the Big Idea 6, Equilibrium. First, let's read the statement for Big Idea 6. This is the overarching statement that applies to Big Idea 6. Any bond, chemical bond, any bond or intermolecular attraction that can be formed can be broken. Everything that can be done one direction can be done the other direction. This seems a contradiction to what we learned in thermodynamic favorability, but even thermodynamically favorable reactions can be run in reverse. Any bond or intermolecular attraction that can be formed can be broken. These two processes are in a dynamic competition, a forward rate and a reverse rate. The rates do not stop. They simply reach equilibrium when their forward rate equals the reverse rate. These two processes are in a dynamic competition. This dynamic competition is sensitive to initial conditions. In other words, the initial concentrations of the reactants and the products, the initial temperature, the initial pressures. All of these conditions will affect the forward rate and the reverse rate. The rate of reactions depend on the concentrations of chemicals. The rate of reactions depend on the temperatures, the pressures of the gases. So the rates of the forward and reverse reactions, this dynamic competition, is sensitive to initial conditions. It depends on initial conditions. It is also sensitive to external perturbations. External perturbations, just a fancy way of saying influences from the outside, such as putting heat into the system, raising the temperature of the system, changing the volume of the system, adding reactant, adding product. Anything you do that changes the conditions of the system will affect the forward rate and the reverse rate, and it will affect this dynamic competition between a forward rate and a reverse rate. When that dynamic competition reaches a point of equality, where the forward rate equals the reverse rate, you've reached a point of equilibrium. Any bond or intermolecular attraction that can be formed can be broken. These two processes are in a dynamic competition. This dynamic competition is sensitive to initial conditions and sensitive to external perturbations. We are specifically going to be interested in chemical equilibrium. A chemical equilibrium is a dynamic reversible state in which rates of opposing processes are equal. So once you have reached chemical equilibrium, your forward rate equals your reverse rate. Let's take as an example the reaction between H2 and I2 to form HI. H2 plus I2 yields 2HI. This is a reversible process because H2 and I2 can collide and make 2HI, and 2HI can collide and make H2 and I2. If I have an empty container and I pump in some H2 and I pump in some I2, the H2 and I2 will begin reacting. So on this graph, we see the reaction rate of H2 plus I2 making 2HI. It's labeled the forward reaction. So the forward reaction begins at a fairly high rate because initially you have the maximum amount of H2 and I2. As the H2 and I2 are used up, the forward rate slows down. The reaction rate for the forward reaction decreases. So that's because you're using up H2 and I2. So we learned about that in kinetics. Rates slow down because you use up the reactants. However, now we're going to throw in the reverse reaction. The reverse reaction is 2HI makes H2 plus I2, the backward reaction. It begins at 0 because you only put H2 and I2 in the container, so initially you had no HI, but HI began to form from the reaction of H2 plus I2. As HI begins to form, the forward rate, or the backward rate, the backward rate begins to increase. The backward reaction kicks in. It begins to rise because the more HI you make, the faster the reverse reaction begins to occur. Over time, at some point in the future, we don't know if that's going to be a few seconds or a few minutes or a few hours, but at some point in the future, the forward rate slows down, the reverse rate speeds up, and they reach a point about halfway through the graph here where they are equal. Now, when you reach that point where the forward rate equals the reverse rate, you are now using up H2 and I2 as fast as you are reforming it. You are making HI as fast as you are using it up. After that point where the two rates have become equal, the forward rate no longer changes because you aren't changing the concentration of the H2 and the I2. They become constant, so the forward rate becomes constant. The reverse rate no longer changes. You have a constant amount of HI, so you have a constant concentration of HI, so you have a constant reverse rate. If the forward rate and the reverse rate are no longer changing and they are equal, the concentrations are no longer changing, you look at the system from the outside, it looks like everything has stopped. Has it stopped? No, it's just going the same speed forward and reverse. It's reached equilibrium. You have an equilibrium state. That equilibrium state may favor products. If this is a thermodynamically favorable reaction, it may favor reactants if this is a thermodynamically not favorable reaction. But that equilibrium state means that from then on, as long as there are no external perturbations, nothing changing from the outside, you are going to have a constant amount of H2, I2, and HI. Now, what are some examples that we might see in this class? Here are three that definitely will come up when we discuss various examples of equilibrium in Big Idea 1, or Big Idea 6, I'm sorry. In many classes of reactions, it is important to consider both the forward and reverse reaction. On the left, we see dissolving and recrystallizing of an ionic solid. The pluses and minuses show me it's an ionic solid. The arrows coming out show me dissolving, but the arrows showing the ions escaping from their hydration spheres and getting back into the crystal show me that recrystallizing is also occurring. If the dissolving and recrystallizing are occurring at the same rate, we have a saturated solution. We have a constant amount of concentration of ions in the water and ions in the crystals. The amount of crystal doesn't change, the amount of solid doesn't change, the amount of ions in the water doesn't change. We say we've reached the solubility limit and no more will dissolve unless we have some kind of external perturbation. So that is an example of an equilibrium. The box to the right here shows an example, upper right, shows an example that could be interpreted as the previous slide, H2 plus I2 making 2HI. And we already talked about how that can be an equilibrium. The central equilibrium reaction for acid-base chemistry, and we are going to spend a lot of time on acid-base equilibrium. The central reaction in acid-base equilibrium is the reaction between water molecules to make H3O plus hydronium and OH minus hydroxide. This is not a very thermodynamically favorable reaction, but in any water solution, you will have a few ions of H3O plus and OH minus. It turns out this reaction is very critical to understanding the equilibrium of acid-base chemistry. So we see from the arrows that this is a forward reaction and a reverse reaction. Anytime you see those double arrows, think equilibrium, think reversible. Let's look at some more examples that are reversible. On the far left, we see that in a bottle of water with the cap on, a container of water with some space above it, you will have evaporation and condensation occurring at the same rate. The evaporation rate equals the condensation rate. Once you've reached an equilibrium between the water and the vapor, the two rates are equal. You can also have a gas dissolved in the water. So if we think of a bottle of soda with the cap on, the carbon dioxide escaping from the water at the same rate as the carbon dioxide returning back into the water to be dissolved in the water. That would be an example of an equilibrium between the carbon dioxide in the space above the liquid and the carbon dioxide in the liquid. And on the right here, we see the example of dissolving and recrystallizing of an ionic solid. This one happens to be calcium fluoride, also known as the mineral fluorite, a purple crystal known to be the state mineral of Illinois. But calcium CaF2 dissolves to make Ca plus 2 and 2F minuses. Once you reach saturation, you create an equilibrium where the dissolving rate equals the crystallizing rate. So many readily observable processes are reversible. Examples include evaporating and condensing water, absorption of a gas, or dissolving and precipitating a salt. We are dissolving the salt calcium fluoride. We are precipitating the salt calcium fluoride. Relevant and interesting contexts include biological examples. So this could be a principle that could be used to understand certain things in biology, AP biology. One example is the oxygen molecule binding to hemoglobin and then releasing from the hemoglobin. So that means it's reversible. Oxygen can go on hemoglobin, oxygen can come off hemoglobin. We think about the receptors that can detect certain gas molecules and give you a sensation of smell. So those sensors, those nerves that can detect the gas molecules, they will attach gas molecules, send signals to the brain that there is some kind of scent, and then they will release those gas molecules. That is the way you can go on continue smelling. If those sensors absorb gas molecules and never release them, then the sensors would no longer be able to work. So they have to absorb those gas molecules, then release them. That's an example of a reversible process. And another example of a reversible process would be the transfer of carbon between the atmosphere, where it is carbon dioxide, and in the biosphere. When the carbon dioxide is absorbed by a plant, it becomes glucose. A sheep eats the plant. The carbon is in the sheep. The sheep dies and decays. Then the carbon gets back into the soil. Maybe the carbon is somehow oxidized to carbon dioxide and goes back into the atmosphere. So this is a reversible process. Carbon can be in the atmosphere. Carbon can be in the soil. Carbon can be in an animal. Carbon can be in a plant. External perturbations like sunlight can affect that equilibrium. External perturbations like making carbon dioxide by burning fossil fuels can affect that. Things like the ocean taking up some carbon dioxide or releasing carbon dioxide in the atmosphere, those can all affect that equilibrium. Also, gases in the atmosphere can be absorbed by the hydrosphere, or the oceans and the rivers and the lakes. Carbon dioxide is one of these. Carbon dioxide can be taken up by the ocean. Carbon dioxide can be released by the ocean back into the atmosphere. And so carbon dioxide is reversible between the ocean and the atmosphere. Once in the ocean, it undergoes a lot of reversible reactions. Carbon dioxide and water to make carbonic acid to make bicarbonate and hydrogen ions, carbonate to make CO3 2 minus and 2H pluses. Of course, carbon dioxide being absorbed into the ocean actually affects the pH of the ocean. It makes it more acidic. But carbonate in the ocean can bind to calcium ions and become part of calcium carbonate, which is a mineral, and make up coral, can make up the exoskeletons or the shells of various animals. And so the transfer of carbon dioxide back and forth between the ocean and the atmosphere, and within the ocean between dissolved in the water and precipitated out onto shells of animals. This is all a very interesting equilibrium to a marine biologist or to an atmosphere atmospheric scientists who are studying carbon dioxide in the atmosphere. Finally, what is this going to look like in this class? These three kinds of reactions are going to be studied extensively in this equilibrium unit. We are going to spend some time talking about dissolving and recrystallizing saturated solutions, and what concentration of calcium ion would you have in a saturated solution of calcium phosphate? What concentration of phosphate would you have in a saturated solution of calcium phosphate? We will spend a lot of time on acids and bases. An acid gives an H plus ion to water to form hydronium ion and A minus. A base like ammonia takes H plus from an acid like water and makes NH4 plus and OH minus. These equilibria, when you have weak acids and weak bases, these equilibria are very important in understanding what is the pH of a weak acid, what is the pH of a weak base, and so forth. So we'll spend a lot of time in 6C on acid-base equilibria. Finally, if you think about the redox reactions and the batteries that we studied back in electrochemistry, that's actually a reversible process as well. We think of it as being thermodynamically favorable in one direction. For example, copper loses 2 electrons to make copper ions that dissolve in the one side of the electrochemical cell, and then the electrons go over to the other side where they reduce the silver ions to make silver atoms. And we know it goes in that direction because E naught for the silver reduction is 0.80 volts. E naught for the copper reduction is 0.34 volts. So it's going to run in the oxidation direction. The silver is going to run in the reduction direction. But that's a thermodynamically favorable reaction. We talked about it as only going in one direction. But it is reversible, particularly if you hook it up and recharge the battery, you're running it in reverse. But if you think about it, this reaction occurring long enough to run down the battery, once the battery runs down, the reaction is actually going in forward and reverse at the same rate. The two reactions are actually occurring at the same rate in both directions. They've reached an equilibrium when the battery loses its voltage. If it never loses its charge, we say that it needs to be recharged. What we're saying is we need to run the reaction back the other way so we can get the reaction to be thermodynamically favorable again. When a battery reaches equilibrium, we throw it away because the battery has lost its energy.